Starting chapter 8, we're going to look at differential equations, and a differential implies that a derivative is involved. And the first couple of examples in today's notes kind of reiterate that fact. A differential equation is something that you're probably already familiar with, but a differential equation in its most basic sense is an equation that involves a derivative. Simple idea? We're almost going back to first semester, but except we're going to use integrals for it. So just as an example, here is an example of a differential equation. Look familiar? And the process, normally the command here is find all the functions y that satisfy that equation. That's really longhand notation for solve or find solutions. And this takes us back, and we did this a little bit in chapter 5. This equation is a derivative. And to solve that differential equation, our job is to, let's do this, given the derivative, find the function. And this is a process, function y. This is a process you should be familiar with, right? If I have the derivative, how do I get to the function? It's right on the tip of your tongue. If I have a derivative, how do I go backwards to the function? Anti-differentiate or integrate, right? Okay, so I'm going to kind of take you the long way through this because this is going to kind of mirror what we do in section 8.3 and 8.4. But to get from a differential equation to the original function, I integrate both sides with respect to the appropriate variable. In this case, I'm going to integrate both sides with respect to x. We're going to take this the long way. There are shortcuts to this, but I want to make sure that we're all good on the process at this point. Okay? Looking at the left-hand side, I have a dx on the top. I'm multiplying, this is dy dx times dx. A dx on the top and the dx on the bottom. So this left-hand side is the integral of dy. More popularly known as, or more easy to deal with, if we called it 1 dy. So that's the antiderivative of 1 dy. The right-hand side, I think we can do. Help me. What's the antiderivative of secant squared? Tan. Antiderivative of 2x? X squared. Antiderivative of 5? 5x. And since it's an indefinite integral, we add a plus c. I'm going to call it c1 for this example. We'll see why in a moment. See why in a moment. Ha. Ha. I'm going to call that c1 because on the left-hand side, what do I have? What's the antiderivative of 1 with respect to y? What's the antiderivative of 1 dx? X. What's the antiderivative of 1 dy? Y. This is y plus, I'm going to call this c2. Okay. Now, that's the mathematically accurate way to take an antiderivative of both sides. If you anti-differentiate an expression with an indefinite integral, you have to add a constant of integration. And we have to allow for the fact that because these things are two separate expressions that we're anti-differentiating, we have to allow for the fact that we could have a different constant of integration on either side. That's the long way. But with the argument I'm about to give, you don't really need both of them. Because algebraically, what do we want to do with this? Solve for y, which is a matter of subtracting c2. And if I subtract c2 from c1, what do I get? If I subtract a constant from a constant, I get another constant, right? Which is an argument for this statement. We could just say y equals tan x plus x squared plus 5x plus just some constant c, and I don't need a subscript. Does that make sense so far? Okay. Notation or vocabulary-wise, this is called a general solution. And it is general because it's got a C on it. It's a family of antiderivatives like we talked about in the beginning of chapter 5. Because there's lots of functions that have that same derivative, right? We just have to change up the C value and we'll get a different function but the same derivative. Kinda? Okay. The next step is to solve initial value problems. An initial value problem is a fancy way of finding a particular solution, aka solve for a C value. And we've done this before. You need a single point on the function in order to determine which function you really care about. So we're going to go through that exact same process of finding a general solution, and then we're going to use the initial condition. That's an initial condition of 1, 0. We're going to use that initial condition to find the particular solution. Okay? Let's go through this one quickly. Integrate dx. Integrate dx. I'm going to shortcut the left. Hopefully, it comes to you pretty quickly that the antiderivative of dy, 1 dy, is y plus c. I'm going to skip the plus c on the left-hand side, though, for reasons explained earlier. Integral of e to the x. E to the x. Integral of 6x squared. 2x cubed, right? 6x cubed over 3 plus constant of integration. That's a c. I should make that look like a c, not an e. It's a c. Okay. What is this called? General solution. How do I make it particular? I plug in the initial condition. I got an x value and I got a y value. So I'm going to say that the y value, 0, is equal to e to the first minus 2 times 1 to the third plus c. Little algebraic magic, and it looks like the c value is 2 minus e. Will you just convince yourself of that before we move on? So the particular solution is y equals e to the x minus 2x cubed plus 2 minus e. I'm going to set that c value off in parentheses. You don't need to. It's not right or wrong either way. I'm going to set it off in parentheses there to just kind of distinguish it as the c value. Questions so far? All right, here's where we pause because it's about to get really way weird different. Okay? At this point, I will pause and say, what we've just done is a really nice method for solving a differential equation when the entire equation is in terms of x. Okay? That's a really nice method for solving differential equations when we have functions. Higher algebra and pre-calc type functions, e to those and polynomials and all those kinds of things. And you can kind of see that that's a predictable idea, right? When they're functions we're familiar with, this process for solving a differential equations is a great way to go. The problem is, if you turn your notes page, we go to this. And I don't want to go into a lot of detail on this today, but this is a differential equation that you can't solve using traditional methods. So we're going to have to find a different way. And we're going to talk about why we can't solve that when we get to section 8.3, and that starts Friday. I don't want to dwell on that today because I think the skill that we're going to learn today is complicated enough that I don't really want to spend time on the why for that today. But that is a differential equation that we cannot solve using an algebraic method at this point. All right? So we are going to draw pictures. This is where it gets fun. We are going to make what are called slope fields. We are going to take the differential equation, the dy dx, and we're going to find some slope values because that's what dy dx gives us, right? Slope values. We're going to find some slope values, and we're going to draw them on a graph, and we're going to pretend that we know what y looks like based on the slope values we get. With me? I like to preface this by saying, has anybody played the old Nintendo Game Boy? Now I say the old Nintendo Game Boy, put your hand down if you've never played a Game Boy that's not color version. You've played the old one. No backlit screen. I had to buy my own special, like, separate LED light that was like weighed as much as the Game Boy, and it came out over the screen. You've seen these, right? My favorite game on the old school Game Boy was a game called Golf. And it's a two-dimensional screen, and it's 8-bit graphics, and you can't demonstrate a putting green on a golf game in 2 dimensions, right? Because what's cool about greens when you're playing golf? They're sloped. They're all over the place. They're up and down and rolling hills and all these things, right? That's how I picture a slope field. Because on this game called Golf, it was just called Golf. It wasn't like Tom Lehman's Super Golf or who was Roy McIlroy's par 3 golf. It was just called Golf. It was just a lame Game Boy game that I loved because when you're putting on the green, you had to see which way the arrows were pointing to see which way you were going to hit the ball to get it in the hole. You with me on this? Okay, good. Someday there's going to be a generation of students that are not going to understand what a two-dimensional video game looks like. So I'm glad you're still with me. That's how I picture slope fields. And we're going to make, on an XY coordinate axis, a slope field that looks like the Game Boy golf game, and it's going to be awesome. All right, here we go. So, and the way we draw slope fields is with little tiny tangent chunks. That's all it is. Okay? So here's what I want you to do. I don't want to make this too big and complicated, so will you label your axes like this? I don't want to make a ton of points on this. I want to make this, that's not what I wanted to do. Let's make this 1. Let's make this 2. Let's make that -1 and down here -2. Okay? And these are also a little easier to do if you make some dots. And because when you get to the AP exam, there's going to be dots. And this grid is going to have a good chunk of dots on it because we're really just going to focus on integer valued coordinates because that's all we're really going to have time to do. It's not worth doing fractions. Because really I just want to, I want to look for trends. I want to look for, if I dropped a golf ball in the slope field, where would it roll to? Kind of a fun little image for it. Okay, make some dots there, would you? Next thing I'm going to do is I'm going to start a little bit of a table. And this is a little bit of a weird table because it's going to be a slope field table. And the slope field will often depend on 2 variables. It'll depend on an x value and it'll depend on a y value. And then once I find the slope, I'm going to draw that slope at the point that I find. Okay? What's your favorite point on the coordinate system? 0, 0. Good answer. Let's say that we wanted to know the slope of this function at the point 0, 0. Could we find it? What is it? It's 0 plus 0, right? Which is 0. So at 0, 0, because it's tied to the point 0, 0, will you draw a mini segment that is horizontal? We've just drawn part of a slope field. Isn't that fun? You feel good about this? You're creating a video game. You're creating a video game for a video game system made in the mid-1980s. It's not exciting to anybody else? Okay. All right, let's pick another point in the coordinate system. 1, 1, great. We might have to pick a lot of these. We might only have to pick a few. 1, 1, the slope will be 2. So at 1, 1, approximate a slope of 2. I guess maybe that would be pretty good. Okay, let's pick another point. You guys are making it too easy on me. Slope is 4, right? Okay, what else? Let's pick something on an axis. How about 1, 0? What's the slope at 1, 0? 1. 1, 0 has a slope of 1. Okay? Now, once you've done a few, you might want to start looking at trends. Is there anything now that's going to be predictable? Predictable in the sense that we really, really, really like slopes that are 0. Why? Because horizontal segments are easy to draw, right? Okay. Where else might I get a slope of 0 besides 0, 0? 1, negative 1, any point where the x and y coordinates are opposites, right? So let's go to 1, negative 1 and draw a horizontal. Let's go to 2, negative 2 and draw a horizontal. Let's go to negative 1, 1 and draw a horizontal. Let's go to negative 2, 2 and draw a horizontal. Cool? What else is going to give me a slope of 1? The slopes of 1 are easy to draw too, right? What else is going to give me a slope of 1? 0, 1 will give me a slope of 1. 2, negative 1. We got 1, 0. Negative 1, 2. Sort of. Okay. What else? What other slopes would be nice? How about a slope of negative 1? What about a slope of negative 1? Negative 1, 0, right? Negative 2, 1, I heard. Is there another one? 1, negative 2. How about 0, negative 1? Yeah? That's a slope of negative 1, isn't it? Okay. Do you see a pattern a little bit? They're hard to see, but there's a little bit of a pattern. Okay. As I get more positive, they're going to be more positive, right? Yep. Diagonals match up. So yeah, here's a nice thing to look at. We're going to spend a lot of time today looking at trends. Those slopes are all 0. Those slopes are all negative 1. These slopes are all positive 1. Okay, we're going to look at trends that way. It's kind of cool, isn't it? So what is this, guys? What is this? This is a graph of general solutions to the differential equation dy dx equals x plus y. Okay? This is negative 2. This is negative 2. This is negative 2. And you can see how that goes, right? Okay? Good so far? How do we move from a general solution to a particular solution? What we do is we set an initial condition. We drop a golf ball. Okay, what curve would be made if, let's say, my initial condition was 1, 0? I put a point at 1, 0. And now I see what happens as I go to the left and the right. As I go to the right, what happens? It's going to rise, right? It's going to get steeper as I go that way? Yeah? Okay so far? What happens as I go to the left? Well, here it's falling, right? It's falling, right? And then at some point, where do I have my horizontals? At some point here, it's going to be horizontal, right? Then what's it going to do? Is it going to go down or come up? It's going to follow the tangents, right? So something like this, approximately. It's not perfect, but we can't solve this one using any algebraic method, so all we can do is generalize and visualize a particular solution, okay? So the big skill today is you're going to be asked to make some slope fields. You're going to be asked to match up some slope fields. I want to give you some tips. Okay? Go to reading a slope field. A few features are going to help you identify what you're looking for. My favorite places are where the slopes are 0. There's horizontal segments wherever the slope is 0. Okay? I also like looking at the x-axis and looking at the y-axis. I also like to look for patterns that where if the slopes only depend on x or only depend on y. Okay? If the slopes only depend on x, maybe you can draw a little picture of this. But if the slopes only depend on x, you're going to have vertical patterns. So all of your slopes at x equals 0 are going to be the same. All of your slopes at x equals 1 are going to be the same. All of your slopes at x equals 2 are going to be the same. So you're going to have vertical patterns when the slopes only depend on x. We'll do one of those again in a little bit here. And the same idea with slopes that only depend on y. If the x is gone, all you care about is the y coordinate. So you're going to have horizontal patterns. So at y equals 0, you might have a slope of -1. At y equals 1, you might have a slope that's trying to be vertical. At y equals 2, you might end up having a slope of +1. So you're going to have horizontal bands when the pattern only depends on y. Okay? So look for those things. I like to find zeros first. And here's your first little quiz. It's not really a quiz, but here's what I want you to try. I want you, with a neighbor, to convince yourself and them which of these graphs is dy dx is sine x plus y, and which of these graphs is dy dx equals sine x minus y. Use those hints above and convince your neighbor that you know which one is which. Let's talk about a strategy. Let's talk about a strategy. What did you use? What did you use? Which of the menu items is most appealing to you? Horizontal slopes are probably the easiest to visualize if you can get yourself there. Horizontal slopes. Based on the functions, now you can go graph to function or function to graph. This is a way of looking at it, okay? Based on sine x plus y, how do I make that function equal to 0 so that it has a horizontal tangent? There's lots of ways to do it. Give me an easy one. Sine something equals 0. Sine 0 is 0, right? Sine pi is 0. Can you imagine how challenging pi might be here, though? Okay, so here's what I'm going to start with. I'm going to go with that. If x plus y equals 0, now there's going to be other places for this too, but if x plus y is 0, I'm going to have a horizontal segment on my graph. Give me a couple ordered pairs that do that. -1, 1. -2, 2. Can I flip these? 1, -1. 2, -2. How about 0, 0? Okay. Can you plot those in your mind? What does that look like? Looks like this, doesn't it? So along this segment, there should be horizontal tangents. Which of those graphs has horizontal segments along that line? A or B? A does. If you look carefully, they're trying to be horizontal along that. I think this is a cool looking pattern over here too. I'm not going to get into what that is today, but I think it's worth looking at. That's kind of what's going on there. It happens again up here. That's so weird. I wonder why. So same idea. If I gave you all the answers, how fun would this class be? So sine x minus y, you think it'd be more fun if I gave you all the answers? You're wrong. It's okay. It's not the end of the world. What about sine x minus y? We want x minus y to be 0. Let's do this one algebraically. If I put y on the other side, I have y equals x, don't I? You know what y equals x looks like, don't you? Along the line y equals x, you've got this pattern of horizontal segments. Does that make you happy? So x minus y goes with this one, x plus y goes with that one. Kinda. If you think you knew how to do that, I want you to spend about 3 minutes on these guys. Right. Couple of things. I mean, these are all kind of basic differential equations. Want to look at some trends. You can either go from the equation to the graph or the graph to the equation. Doesn't matter that much. You want to be able to play around with some of both of these. I like, number one, I like looking at the equation because I love when slopes are zero. When are slopes going to be zero for equation number one? Slopes are going to be zero when x and y are the same, right? You with me on this? So now I'm going to look for a pattern of horizontal slopes along the line x equals y. Do I have horizontal slopes along x equals y there? Bummer. Do I have horizontal slopes along x equals y here? Yes. How about on C or D? No. So this one, I'm going to be able to connect up with equation number one. Does that make sense? Okay, but you can't always, it's not always that easy to go from equation to graph. Let's look at one that goes from graph to equation. Let's look at graph A. And again, I'm looking for patterns. This is kind of a mess on graph A. And I look for horizontal slopes. Where does it look like the graph is trying to have horizontal slopes? It's trying to have horizontal slopes right here. So horizontal when x equals 0, okay? Trust me, Siri does not know the answer to the slope field questions we're about to dig into. So I've got that idea. I've got the horizontal when x equals 0 thing going on. So what about the other axis? I think it's worth looking here. What are they trying to do on the horizontal axis? They're trying to become vertical. Vertical when y equals 0, okay? Go back to your old algebra slope formula. Slope is change in y over change in x, or rise over run, or in this case it's something weird. But how do I get horizontal when x is 0 and vertical when y is 0? Which equation? Equation 3. Does that make sense? Look for trends that way. Are they all going to be that nice? No, probably not. Okay? Are we okay with these, or do you want me to keep going? You okay? C goes with equation 4. D goes with equation. This goes with C. This goes with D. So B, D, A, C, right? Okay. I want to start you on the slope fields worksheet. I want to do it for these first two together. And then we'll be done for the day. So, first equation, dy dx equals x plus 1. If you want to, you can make a little table. Ordered pair xy, dy dx here. Okay? What's your favorite ordered pair? 0, 0. Why? We should start at 0, 0 all the time, shouldn't we? We can't always, but it's really good to try. So at 0, 0, what's the slope? 1. So make a little segment that has a slope of 1. Okay? Now, you can do a couple of different things from here. I think it's a good idea to play on the axes first. But if you think you might see a pattern, go for it. Okay? I might next try 1, 0. What's the slope going to be at 1, 0? 2, right? A little steeper. What's the slope going to be at 2, 0? 3, a little steeper yet. You see the pattern? Slope went 1, 2, 3. What's the next one? Probably 4, right? These are approximates now. What happens if I go the other way? What's the slope at negative 1, 0 going to be? 0, negative 1, negative 2. Kind of see a pattern there? Okay. Let's try the other axis. Let's try 0, comma 1. What's the slope at 0, comma 1? 1. What's the slope at 0, comma 2? 1. What's the slope at 0, negative 1? 1. What's the slope at 0, negative 2? 1. We talked about this not too long ago, but you're not going to get it until you see it a couple of times. What's going to happen? What's going to happen for all of these values at x equals 1? They're all going to be slope 2, right? Slope 2 here. M equals 2 there. M equals 1 there. All of these are going to be horizontal. This is about to get really cool. This is about to get really cool. What's happening here? Negative 1, negative 1, negative 1, negative 1. Negative 2, negative 2, negative 2, negative 2, negative 2. Do you see it? Whenever the differential equation only depends on x, you're going to have vertical bands. You're going to have vertical pattern. These are going to be steep. Okay? Now, you're not asked to do this. This is a graph of the general solution. You're not asked to do this, but I want you to because I think this gets really, really cool. How do you draw the particular solution? Let's say I had an initial condition of 0, 1. I drop a golf ball at 0, 1. Do you kind of have a feel for what that golf ball could do if it went either way? Do that again. It's going to do like something like that. Tell me why in the world, some of you said parabola. Tell me why in the world a parabola would make sense here. Okay, on the graph it makes sense. It looks like it should make a parabola, right? Let's talk about the equation. Why does the equation lead us to the reasonable belief that the y function should be a parabola? dy dx is a linear function, and if the derivative is linear, the original function is probably a quadratic. Are you with me? And tell me this isn't cool. Okay, fine. Have it your way. It's not that cool. I think it's awesome. Because everything is awesome. Okay, let's do one more. I should bust out into the Lego song, Everything is Awesome. Okay, what do you notice? Let's do one more. dy dx is 2y. The derivatives depend on the y value. So when y is 0, what are the derivatives going to be? 0. So y is 0. You're going to have a bunch of horizontal segments here. Good? What about when y is 1? 2. Slope is 2, slope is 2, slope is 2, slope is 2, slope is 2. Okay? What about when y is 2? Slope is 4, right? You're going to have these are not quite vertical. Don't make them vertical, but they're steep. Okay? What about y equals negative 1? Negative 2, right? What about these? Okay? These are going to be even steeper. Those are going to be a slope of 4. Drop a golf ball. Drop a golf ball, I don't know, over here somewhere. Do you see that the golf ball is going to do that? What if you drop the golf ball up here? Golf ball is probably going to do that. Okay, this is a weird one. But that's what slope fields do. They graph general solutions, and if we put a particular solution on as a starting value, we put an initial condition on, we can have a sense of where it's going to go. Tonight, there's the slope fields worksheet. Tomorrow, we start class with tests back and FRQs.